All right, I'm going to try to give you a quick review of plate tectonics. Now, this is a topic that is found in APES Unit 4.1. There's also some videos on your MyAP site that you could watch on this topic as well. This is also covered in Chapter 14 of your ebook, and we just don't have the time this year to cover this topic in class, so I wanted to race through it here in a quick lecture for you. First, to understand plate tectonics, I think it's easier to understand the evidence that we have for it. So this is some of the evidence that we have. I'm going to just go over this. So the first piece of evidence that we have is fossil evidence. And for instance, this first species here listed, Ceanothus, this is not a species of organism that swims. So therefore, for it to be on both sides of the Atlantic doesn't really make sense. It's the exact same species, but yet it can't swim, so how did it get on both sides of the Atlantic Ocean? The next one, Glossopteris, in green here, this one also is found in South America, Africa, India, Australia, and even Antarctica. This is a swimming species, but it's a freshwater, not a saltwater species. So scientists are asking the question, how could this creature get on 5 different continents when it can't cross the ocean? So one of the things that made sense was perhaps all of these continents were actually touching at one time. Okay, some other evidence that we have is coal deposits in Antarctica. Now, this doesn't make sense because coal is created by organic material, plants, trees, animals, and those things dying, decaying, being compressed over long periods of time. That's how you get coal. But this is Antarctica at the South Pole, so it's way too cold to have all these plants and animals. So the theory is, well, perhaps the continent of Antarctica was further towards the equator at one time, so it was moving. And then similarly, glacial deposits in Australia. Australia is at a latitude right now where glaciation is not possible. It's not cold enough. So scientists propose, since we have evidence that glaciers were in Australia at one time, perhaps the continent of Australia was closer to the poles at one time, making it colder. So all of these things would mean that these continents are going to have to be moving, and this is the stuff that supports the plate tectonics theory. This is a video clip that shows how the continents moved around the planet through the history. Like this is 2.9 billion years ago, and it shows how the where the continents are, how they move, how long it took for them to develop, stuff like that. It's pretty cool to watch. I usually try to watch this at twice the speed here, but we can just speed it up this way. So you see here, so up. Okay. All right, so you can see here, this in the green, there's a little key over here. In the green, you've got, this is actually North America. The purple, that's Australia. So you can see these continents are moving around all over the planet here. There's a supercontinent there. Move ahead. Let's move way ahead. Supercontinent is Gondwana there. See Africa down here near the South Pole. Here's North America. Okay, now we've got the famous Pangaea. Now you can see things here. There's South America, Africa, and there's North America there. And kind of interesting North America. So right here, North America splits apart. So we've got an ocean running through North America here, and this could be how the Rocky Mountains formed. And you see it closes up there, comes back together, and then we've got our continents all in the places that we recognize. All right, we have two different kinds of crust, and the type of crust impacts how plate tectonics works, so it's good to know the difference between these. Now, the ocean crust is heavy and we'll say dense, while the continental crust is light and fluffy. How's that? Light and fluffy. Okay, that's the big difference between the two. And there you can see where they are located in this model. And then as far as plate boundaries go, we've got boundaries where we have two ocean crusts coming together, like we do at this in the middle there, and then over here on the right. And then we've got ocean continental crust boundaries, where we've got some ocean crust meeting up with some continental crust meeting up with some ocean crust. All right, now since the ocean crust is heavy and dense and the continental crust is light and fluffy, the continental crust goes to the surface and the ocean crust sinks beneath it because it's more dense. Okay, so we see the continental crust on the surface, the more dense ocean crust sinking beneath it. Over here on this side where you've got ocean crust slamming into ocean crust, one of them has to be more dense than the other, and the more dense one is the one that will sink below. Okay, at these boundaries you get two different features. You get these ocean ridges and you get these trenches. The ridges, this is where ocean crust is created. We've got magma rising up from the mantle here. That gets to the surface and then pushes to the side here. All right, and so we've got new crust there at the ocean ridge. The crust is being destroyed where you've got these one crust being subducted under another crust. Okay, we call those subduction zones. And again, so we've got this crust that's moving down below like this, okay, causing this subduction because you've got the lighter, less dense crust sitting on the surface there. Okay, as this crust is being subducted and it's moving, it's creating this friction with the other plate. And that's going to heat up the rock, and you're going to get melted magma actually created because of the amount of friction that's there. And then these guys are like little hot air balloons. Hot air balloons rise because they're less dense than the air around them, and these pockets of magma do the same thing. You got this hot magma, it's hotter than the rock that's around it, so therefore it's less dense and it wants to rise, and it's going to try to rise up through the rock here. Okay, and that's how you're going to get volcanoes in those subduction zones. So, where do we get volcanoes around the planet? We get it at subduction zones and at ocean ridges. Okay? All right, now the other boundary where you have a continental crust meeting up with a continental crust, or I shouldn't say meeting up, I should say slamming into, because these crusts have similar densities, you don't get subduction. You get more uplift. You get tall, tall mountains, all of the crust pushing up. And you really don't get the subduction that we have at the other boundaries. Okay, that means if there's no subduction, that means there's no friction underground, and that means that you're not going to get volcanoes at these continental boundaries. Think of the Himalayas. The Himalayas are a continental boundary. You got the tallest mountains on the planet, but you have no volcanoes. That's because it's continental crust with similar densities, and you're only going to get uplift, no subduction. If new crust is created by plate tectonics, why isn't the Earth's crust getting thicker? The reason is because it's created at the same rate that it's destroyed. So it's being created here at the ridges and then being destroyed in the subduction zones in the trenches. So it balances out. All right, so you've got crust being created at ocean ridges. That's where the youngest crust is because it's brand new. And there's a plate boundary. There's a different crust on each side of the ridge. So here you've got the ridge running through here. So you've got a different plate boundary, different plate over here and over here. I think I show this here. So there's the ridge, and then you've got the South American plate and the African plate running right through at the boundary between the two there. You should be able to look at a map like this that shows elevations through the oceans, around the planet, and figure out where the new crust is being created around the planet. I've told you that the new crust is being created at the ridges, so you're just looking for these ridges out in the middle of the oceans. So you can see one here. This one runs up and slices through Iceland. And you've got this one along here. So this is where new crust is being created. A lot of it going on out here. You can see it through here. Okay? New crust. So therefore, if you were asked a question like, where's the youngest crust in this map here, orient yourself. The gray parts, those are the continents, and then the colored parts, that's the ocean. The red parts, those are the ridges, like this ridge here running through the Atlantic Ocean. That's the Atlantic Ridge. So where would it be the oldest, A, B, or C? Well, it's going to be the oldest the further you get away from the ridge, because it's brand new at the ridge, so A here is the furthest away. That's going to be the oldest. And the youngest would be B, because it's right next to the ridge, where the brand new crust is being created. Okay, the crust is destroyed in the trenches at continental ocean plate boundaries, ocean-ocean plate boundaries, where you have subduction. The most dense crust is going to sink below. Here's a mid-Atlantic ridge where new crust is being created, just another model of what's going on. Where is the youngest crust in this model here? It's going to be the stuff that's closest to the ridge. Okay, again, just reminding you where the volcanoes are occurring, and they, of course, would be here, here, and here. Where they're not occurring is at these continental boundaries. Okay, I'll let you go through that question yourself. Don't worry about this one. I think it'll just be confusing. Okay, the movement between plates is put into three different categories: convergent, divergent, and transform. Convergent plates, just like it sounds, these are two plates that are slamming into each other, as all of these models show here. This plate moving this way, this plate moving this way, slamming into each other, with the most dense crust being subducted under the other. And here, this top one here, we'll call this A, you've got ocean crust, more dense, going under continental crust. Here you've got ocean crust and ocean crust, the more dense ocean crust going beneath. And then here you've got continental and continental crust. So you're not going to get volcanoes, you're not going to get friction, but you do get really tall mountains here. Okay, that's a convergent boundary. Two plates slamming into each other. Okay, divergent boundary, pulling away, creating new crust. Kind of interesting, these different kind of ridges that you have, but kind of interesting that the ridge runs through Iceland, as I said earlier. The mid-Atlantic ridge slices right through it. And you can go to Iceland, and you can see that. Here is a aerial photo of part of the mid-Atlantic ridge splitting up Iceland, with the crust on this side moving this way. This is Eurasian plate, and this is the North American plate over here. Crazy, huh? And you can also go snorkeling in the mid-Atlantic ridge in Iceland, which I did with my family. Pretty crazy and very cool. Worth the trip. Okay, the last kind of boundary is a transform boundary that's moving side to side away from each other. Okay, here they are: summary, divergent, convergent, transform. And so you should be able to look at a map like this and figure out which boundaries do you have, which ones are convergent, which ones are divergent, which ones are transform. For instance, you've got a transform here, you have a divergent boundary here. Of course, out here in the Atlantic Ocean, you've got the divergent boundary at the ocean ridge there. And then you have convergent boundaries, like here, like the one here, creating the Himalayas mountains. Okay. This is showing the transform boundary there at the San Andreas Fault. This crust down here, let's say Los Angeles, is moving north, and San Francisco is moving south. At some point, the two are going to be next to each other, believe it or not. Be a couple 100 million years, probably. This is the San Andreas Fault. This is a couple days ago when I was out there visiting. I took this picture. No, not really. This is from that movie, San Andreas. So this is complete falsehood here. But you can see the transform boundary doing its thing here, moving this curb. Crazy. There's an aerial view of it. You can see there's your transform boundary. Somebody's been marking the dates and showing how fast it's moving. Here you can see that this used to be part of this river here, but it's been offset by this transform boundary. Now it flows like this now. But yeah, so it changes the flow of rivers. This poor farmer did his plowing, and then the boundaries moved, which would be kind of frustrating. Okay. So here's another question from an old AP test. So the big question that the scientists had when they first were coming up with this plate tectonics theory was, okay, so the plates are moving. It appears that they have moved, but what could make them move? And the answer is convection. And we know that in a hot house, or burning house, sorry, the hot smoke rises to the top and the cool air is on the bottom, which is why they tell you to stay low in a burning house. You're boiling water, the hot air, the hot water on the bottom rises to the surface quickly, cools, and then it sinks back down again. This happens with a sea breeze, so you get the land heating up very quickly, much quicker than the ocean, so you have this hot rising air over the land going up in the atmosphere. On the other side, the cooler air, after it goes up way up in the atmosphere, cools down, and then it sinks. So you have this convection going on here. At your house, the cooler part of the house is in the basement, hottest part is at the top because the hot air is less dense and it's rising. Okay, and last example here are these lava lamps. You've got the light source down here that heats up the wax. Those wax balls get heated now, they expand, they're less dense, so they rise up through the oil. And when they get to the top, they start to cool down, and eventually they start to work their way back down again. That's convection. Okay, so what's pushing the plates around? It's convection currents in the mantle. You've got the hot stuff down here near the core, and that hot magma is going to rise. Once it gets to the surface, it starts to cool down. As it gets here, it becomes more dense, and it starts to sink. And so the movement then, this movement here is pushing that plate in that direction. So it's the direction of the convection flow. Again, here, convection going this way, pushing that plate in that direction. Same thing here, moving it this way. The cooler magma sinking, hotter magma rising, and creating that current that's pushing this plate in this direction. Okay, that's what's pushing the plates. You can see it in a better model here. Hot down here near the bottom, rises up, cools down, and then sinks. And that convection is moving this plate in this direction, moving this plate in this direction. Why is there no subduction at that location? It's because those are not two plates converging. This is one big plate. So plate can't run into itself. So, wait, I made that too big. This is one big plate. This is another plate here. So these two crusts are part of the same plate. You do have a continental boundary here, so you're going to get tall mountains and no volcanoes. And over here, you've got ocean crust sinking beneath continental crust, so you've got subduction, you've got friction, you've got melting rock, and therefore you're going to have volcanoes above there. Why is the magma rising? Because it's less dense. Why are the tall mountains over here? Well, that's because the continental boundary. And that is plate tectonics.